Okay, so in this video, I'd like to cover just a few weird quirks of the definition here, and I hope this isn't. I hope this doesn't overcomplicate things, but it is important to be aware that this kind of thing can happen. So, um, in the definition of uniform convergence, we let S be a subset of the domain of F. Okay. So the domain of F itself can already look pretty weird. I mean, it's sort of like an arbitrary subset of R, and then S is kind of this arbitrary subset of the domain here. And so like strange things can happen. So for example, so strange things can happen if S is, strange enough. Oops. For example, if S is just a singleton, let's say, I don't know, A, for some A in the domain of F, then F is automatically uniformly continuous on S, even if it isn't continuous at A. Okay, so this sounds really strange, and it is kind of strange. It's unfortunate. I think it's unfortunate that the definition is made this way, although I'm not really sure exactly what the best way to fix it would be. But it is unfortunate that this is possible. You would like for uniform continuity on a set S to automatically mean that F is also continuous on the set S, but that's not necessarily true because S is allowed to be smaller than the domain of F. So, for example, if F is the function f of x is 1 for x equals 0 and 0 otherwise. So in this case, right, the domain of F is R. And S is just the set containing the point 0. Then F is uniformly continuous on S, but not continuous at x equals 0, right? Clearly, it's not continuous at x equals 0, right? Because the graph of this is just like there's a missing point here, and then it goes off infinitely in either direction. So that's like kind of an obvious discontinuity there. Now, what do I mean when I say, so why is it uniformly continuous on S? Okay. And I want to be very clear also that this is not, you should not think of this as saying that F is uniformly continuous at the point 0, okay? Because there is no such thing as uniform continuity at a point, okay? This is just a situation where S happens to contain only one number, okay? So don't call this like, don't ever say, okay, let me just make this very clear. Never say uniform continuity at a point or anything similar. So like F is uniformly continuous at x naught, or whatever, right? Anything remotely like this, don't say that, because it doesn't make sense. Okay. Of course, but we are allowed to consider the case where S just has a single number in it. I mean, that's perfectly valid. Um, it's just that it's not like useful at all. Okay. I mean, nothing useful will come from considering sets that have a single element, but I just want to point out that like this can get more complicated because S could be like a more complicated set where some of the points in S just happen to be isolated. And if there are other points nearby those points where F is actually defined, but those points are not in S, then there can be this disagreement between whether F is uniformly continuous or F is continuous at that point. Because yeah, so like this example kind of illustrates that, right? Because here it's like, why is F not continuous here? It's because there are points nearby where F is defined, right? F is defined at all the points nearby, and F is equal to 0 there, right? So the domain of F includes all these points nearby, but S itself does not, right? And if you go back to the definition of uniform continuity, we only require, so in the definition of uniform continuity, we only require f of x minus f of y for x minus y less than delta for x and y in S. Okay. So basically it's like in this situation, right? Since S only has one element in it, for x and y both to be in S, then x just has to equal y, right? Like, yeah, there are other points in the domain of F nearby where, that are within distance delta away, but none of those points are in S, right? S is a subset of the domain of F. And S only has a single point in it. So the only possible like situation where we have to check, oops, this is supposed to be less than epsilon. The only situation where like we have to check that f of x minus f of y is less than epsilon ends up just being where x equals y in this scenario, right? If S just has a single point in it, we only have to worry about like, one possibility, which is if x equals y equals 0. But obviously f of x minus f of y is just 0 in that case. So, it's automatically less than epsilon. So any choice of delta works, right? Any choice of delta for whatever epsilon you pick, any choice of delta will work, and this will be uniformly continuous on this single point set. It's just discontinuous at that point in the larger context of its domain because there are other points nearby where it's defined, but those points are not included in S, okay? I hope I made that clear. I know it's like, this is a very technical thing. I mean, it's just like a real weird technicality of the way the definition is phrased that this is possible. Okay, so what's the upshot, or what's the bright side? On the bright side, we are generally only concerned with cases where S is an interval. In such cases, if S is a subset of the domain of F, and S is an interval, then if F is uniformly continuous on S, well, then F is continuous on S. Okay, so if S happens to be an interval, then you can conclude from uniform continuity that F is in fact continuous as well, okay? And you might want to actually think about why that's true, all right? Like, how would you prove this? It's not hard to prove at all. It's very straightforward to prove this. That if S is an interval, then you can make this conclusion, okay? The other situation where you can make this conclusion is if S is the domain of F and F is uniformly continuous on, did I accidentally say uniformly convergent? Oops. Oh boy. All right, that's going to happen. I'll try to keep that from happening as much as possible. Yeah, my apologies. Just, you know, be prepared that you might have to fill in the blanks every once in a while. But yeah, I'll try to be careful about that because, I mean, obviously it's a very important distinction. All right, anyway, so if S is the domain of F and F is uniformly continuous on S, then F is continuous on S as well. Okay. So this is true. This is true regardless of whether the domain of F is an interval or whatever. The domain of F can literally be any set. And if F is uniformly continuous on that entire set, then F is continuous on then F is continuous on that set. So if F is uniformly continuous on its entire domain, then it's continuous on its domain. This is the other situation, that the other important situation where you can conclude that uniform continuity implies ordinary continuity. Okay, so yeah, I'm sorry that this whole business, I mean, it's kind of a pain in the neck, but yeah, you know, if this, well, I don't know, I don't want to advise you to ignore this because it can matter sometimes, but maybe don't worry about it too much for now, and come back to this if you ever find yourself in a situation where you're confused about whether or not F is continuous, given that it's uniformly continuous or whatever, anything like that. So anyway, yeah, so in the next video, we'll look at some actual examples of showing uniform continuity or disproving uniform continuity, and then we'll move on from there.